Good day, grade 11 chemistry students. Today we're learning about something called intermolecular bonding. See, you didn't know this before, but you've learned about intramolecular bonding. We're going to learn about something called intermolecular bonding today. Okay, so what is the difference between intra and intermolecular bonding? And earlier I said this is what we've been studying intra, okay, molecular. We've studied that before. We haven't studied intermolecular bonding. Well, the difference is this. So intramolecular bonding is bonding within compounds, while intermolecular bonding is the bonding between molecules. Let me show you what I mean. Shazam! We have two water molecules. Now there is bonding within each one of those water molecules. So this represents the bonding within the molecule, okay? This bond right here. But we also have a bonding between the molecules, which is intermolecular, between the molecules. There is an interaction. I'm going to use a dashed line to represent the intermolecular bonding. Now there's different types of intermolecular bonding, and that causes the molecules to stick together, okay? So the molecules that hold, make the bonds within it, they are intra. The bonds within it, the bonds between them are inter, okay? So when we're talking about intermolecular bonding, the stronger that bond is, the more likely it is to stick together. Make sense? So if they're really, really sticky, that means that they are going to have if they have high inter, so I'm just going to represent this by an arrow, up, high inter, that means they're going to have a high boiling point and a high melting point. This means that it's more likely to stick around as a solid or a liquid, okay? It's less likely to be a gas, because remember that solids and liquids are close together, okay? So the more you are sticky, or the more you like hanging out with your buddies, the more likely you are to be a solid or a liquid, and that's dependent on how strong the bonds are. Okay, so let's look at these three examples. We have methane gas. This is natural gas. It heats your home, okay? Then you have propane gas. This is the gas that is used in your barbecue. And finally, we have octane, which is gasoline, which you use in your car, which is a liquid. So what can we assume about this? Well, we can assume that because methane is a gas, propane is gas, and octane is a gas, which one has the highest boiling point? Well, the answer is octane does, because it's a liquid at room temperature, whereas methane is a gas. So therefore, it's already boiled. It's already a gas at room temperature, whereas octane, it actually turns into gas at a little bit higher. Okay, so what is it about these molecules, octane, what is it about octane itself that makes it more likely to stick together? Why does it like to hang out together? Well, their answer is that it has a stronger intermolecular interaction between molecules. So if you take a whole bunch of octane, you fill up your tank when you go to the gas station, they stick together for some reason. Whereas if you filled up your gas tank with methane, it would be a gas. It wouldn't stick together. They'd be farther apart. So we have three types of intermolecular bonding, folks. The first one is van der Waals. Second one is dipole-dipole, and the third one is H-bonds. So as we go down, van der Waals is the weakest, or also known as London forces. Dipole-dipole is stronger, and H-bond is the strongest, okay? So the stronger the bonds are, the more likely you are to be a liquid, okay, or a solid, or in other words, the more likely you are to have a higher boiling point or melting point. Let's talk about van der Waals. So van der Waals is the weakest intermolecular force, and occurs between all atoms because of their protons and electrons. So all molecules have positive charges and negative charges, and most of the time they're attracted to just each other within that molecule, but every once in a while different molecules have protons and electrons that are attracted to each other. Let me explain what I mean. So if we look here, what happens is we have protons within this molecule, okay? within those atoms there. There's a positive charge within every single one of these atoms of this molecule of methane or CH4. Well, there's electrons over here. This proton and this hydrogen has a little bit of an attraction to that electron over there, okay? It's sort of like an unfaithful boyfriend or girlfriend, ladies and gentlemen. There's an attraction there to the opposite sex, even though it shouldn't happen. There is an attraction there, and that is van der Waals force that exists between separate molecules between protons and electrons. And basically, guys, if you have more protons and electrons in a molecule, that means that you are going to have a stronger van der Waals force. So if we look at this example, octane has the highest boiling point because it has the most atoms. And because it has the most atoms, it has the most protons and electrons, okay? So therefore it has more positives to attract more negatives between molecules, okay? So if you take something like octane and we double the length of that, what do you think will happen? Well, we went from a gas, and then propane's sort of a liquid when you put it in under pressure in your propane tank, and octane is a liquid. Well, if you increase the length of octane, you add more carbons and hydrogens to the molecule, you'll actually get animal fat. And we know that if you fry bacon in a frying pan, that it will actually turn solid after you're done frying it. So that's because it has more protons and electrons. So as the carbons and hydrogens increase, greater van der Waals and more likely to be a solid. So next we have something called dipole-dipole forces, which occurs between molecules that are polar and have something called an overall dipole. I haven't really talked to you about this before, so let's look at ammonia, NH3. It's got 3 dipoles. Recall that this dipole here cancels out with this dipole here. So the overall dipole of this molecule is that in general, the electrons are moving in this direction. It has a negative end and a positive end. So this is NH3 here, and we have this overall dipole. So if we take a bunch of NH3s, okay, so if we have a bunch of them, what will happen is that there'll be an attraction between them. So take a look. So I got a bunch of NH3s. Well, what will happen is they will line up, and the negative and positives will sort of arrange themselves like mini magnets, okay? There will always be an attraction between the positive end and the negative end of the molecule themselves. So again, this is what we call a dipole-dipole interaction, and the reason is you have a dipole here, overall dipole here, and overall dipole here, positive end, negative end. Good girls like bad boys. That's the way it's always been. That's the way it always will be. And this is what we have here is we have this stronger attraction that occurs. The last type of interaction that we have is something called hydrogen bonding. It's the strongest type of bonding, and it's actually the bond that holds together your strands of DNA, okay? It's the strongest force that holds different molecules together. It occurs when you have a highly electronegative atom bonded to a hydrogen, okay? So if you have an example in your molecule, if you have an O and an H, an N and an H, and a Cl or H, that can have hydrogen bonding. And what it says is the lone pairs of the electronegative atom are attracted to the hydrogen in other molecules and vice versa. So this is an example of hydrogen bonding. Recall that hydrogen likes to have 2 electrons to have a full shell. Okay, so hydrogen has 2 electrons here, but those electrons are actually getting pulled towards oxygen. So hydrogen, like an unfaithful partner, says, hey man, I'm losing my electrons. Is there any electrons around here that I could borrow? Well, it finds a lone pair in this electronegative atom, okay, and it's attracted to it, okay. So you have a highly electronegative atom and a hydrogen bonded to it. So similarly, each water can actually make as many as 4 of these hydrogen bonds. Now, when it makes 3, it's actually water, okay? It's actually, sorry, yeah, it's water. Obviously, it's water. It's a liquid, okay? That's what I'm trying to say. And when it makes 4, it actually is ice, okay? So that's pretty cool because when water makes this 4th hydrogen bond, actually what it does is it kind of like stretches its arms out. It actually expands. So ice is actually less dense because it expands when it makes this 4th H bond than liquid water. And so as a result, when you freeze, guys, if you take something and you throw it in your freezer, it will explode sometimes because the ice expands. It takes up more volume because of that scenario. Okay, so quick lightning round, ladies and gentlemen. Methane has a boiling point of negative 164. Chloromethane has a boiling point of negative 24.2 degrees Celsius. And what's this? Methanol has a crazy high boiling point of 65 degrees Celsius. So as I go in this direction, my boiling point goes up like crazy. Now, why is that? What intermolecular forces exist between each one of these molecules? Pause the video and try and figure it out. Now, all these molecules are right around the same weights, but the weight isn't really impacting here or anything. The first thing we notice is no dipoles in methane, no electronegative atom in hydrogen, so we can say it just has van der Waals, and van der Waals is the weakest force, so it's not very held together very well. If you have like a billion methanes, they're not going to stick out together. So the boiling point is negative 164. You don't need a lot of energy to separate them. Next, we have chloromethane, which has a dipole. It's a polar molecule. So therefore, it's also going to have dipole-dipole interactions, which really brings up the boiling point a ton because you have positive-negative interactions between a whole bunch of chloromethanes. They're going to stick together like positive and negative, sort of like little magnets. And finally, we have another huge increase because we also have, this is a polar molecule. It has van der Waals because everybody has van der Waals because you have electrons and protons. But the most important thing is you have an electronegative atom and hydrogen. It is, ladies and gentlemen, it is going to have H bonds, and those H bonds really impact it a ton, bring up the boiling point. That's it. There'll be some questions for you guys to work on tomorrow. Enjoy your evening.
Don't you rock my boat.